Dzień dobry. What you can see up here is called the Romanesco, and the Romanesco is a cauliflower. It's basically a vegetable, and Mother Nature made it look really impressive. Basically, it's a cone, but its surface is covered with more of these cones. And you can basically think of it as kind of a component. So it just keeps repeating it itself. If we look at frost under the microscope, we can see similar shapes. And looking at a snowflake under the microscope, we can see that it's actually symmetrical, and it's a lot more detailed than just being this fuzzy ball that we know. A sea urchin has repeating patterns at different scales, and a tree is basically just a stem with branches, while a branch could also be a stem with more of these branches. A lightning tries to find the path of the least resistance while it splits in different directions. And all these pictures that you've now seen have one thing in common. They're what we call fractals. My name is Gregor Adams. I'm a web developer and front-end architect at Sinnerschrader in Hamburg, Germany. And today we're going to be exploring fractals and CSS. So we already know what a fractal looks like, but what is the definition of a fractal? Nowadays, we don't ask the professor, but we actually ask Wikipedia. And Wikipedia told me that a fractal is actually a natural phenomenon. That is what we just saw on all these pictures. But it could furthermore be a mathematical set that exhibits a repeating pattern. And it displays at every scale. And also, if the replication is exactly the same at every scale, it is called a self-similar pattern. And I want you to keep all these key points that I marked here in mind. I've been amazed with fractals for quite a while now, and it basically started with the Mandelbrot set. The Mandelbrot set actually plays a big role in the case theory. To me, it's actually just the most impressive fractal, and I guess it's also the most explored fractal. But it can never be fully explored, because with the Mandelbrot set, each coordinate has different patterns. And while we zoom into it, we can see more and more detail. It also has a lot of valleys. Right now, we are approaching the Seahorse Valley. And if you look at it in detail, you can see that it's just another Mandelbrot set, or basically it's called the Mandelbrot bug or Mandelbrot lake. And it's surrounded by all these seahorse-like shapes. And speaking of a seahorse is actually just another fractal. So this is a picture of Benoit Mandelbrot. Sadly, he died in 2010. Fun fact, he was actually born in the city. So he's Polish, and he was born here in Warsaw. The fundament for the Mandelbrot set exists since 1905, but it didn't really get popular until Benoit Mandelbrot released a study in 1980. And since that day, people have implemented the algorithm in nearly every programming and scripting language. I put a link down here, and it's from Rosetta Code, and you can actually see all these implementations. One of these implementations is a contribution that I made. And I thought I'd contribute a Sass version. This is just the entire code. So this is the actual code that will render the Mandelbrot set in CSS. So let's look at it in detail. You can basically compare it to something like the JavaScript version. What I'm doing is I have a global variable, and I have this mixin, and while I run the mixin, I'm just appending a box shadow to an empty list. So in the end, I just have a really, really big box shadow. This is the actual algorithm. And so what I'm doing is I'm taking every pixel from 1 to the canvas width and from 1 to the canvas height. and then I'm running the algorithm. And when I'm done with the calculation, I'm calling the mixin. So now I'm appending another box shadow. In the end, I have an element. It's just some custom element with some attributes, so I can display it, and it's only on one element. And I'm rendering the box shadow. So in the end, I get this. This element has 160,000 dots, so it also has 160,000 box shadows. I ran 20 iterations on this, and it took 5.5 hours to compile. I did this with Ruby Sass, and I tried doing it with libsass, and I thought it would be a lot faster, but libsass just stops after about half an hour, so sadly it doesn't work. On the following slides, you're mostly going to see the red box on top. The red box on top, if you want to see the slides later online, is always going to bring you to a link to CodePen so you can actually see the code. And my experiments, I have a lot of experiments, so make sure to check them out. And on the lower left-hand corner, the yellow box brings you to a pre-compiled version, because obviously you can't compile this in an online editor. The thing with the Mandelbrot set is the number of iterations actually define the detail that the Fractal has. So I tried to get more detail and a faster compile time. So I made another version. I did this one in color. And it also has 160,000 dots. I ran 70 iterations, and it still took 3.5 hours to compile. I did another Fractal that's similar to this one. It's the Barnsley Fern. I just did this recently. I made this one especially for this talk. And it's generated from random numbers. And the drawing process is quite similar to what I did with the Mandelbrot set. But while I did this, I figured out there are probably better languages to do this than do this in Sass. This entire thing is based on the chaos game. And I'm not a mathematician, so looking at this is chaos enough for me. And one thing I also learned is that chaos and Sass are not friends. But luckily, there are different systems to actually draw a fractal. We have the iterated function system. This is what the Barnsley Fern is generated with. And then we have the Lindenmayer system, which is shortly called the L system. And with the L system, we can actually do more usable, or maybe not usable, but easier to implement fractals. So I went, and the first one that I did on the L system was the Sierpinski triangle. And it allows to use reusable components. And I mentioned in my first slide that basically a fractal is just similar to a component. So this is the entire code for the example that you just saw. And while the CSS gets smaller and more usable, and this is just a small snippet, but the HTML gets really, really big in the end. So as you can see, I have just a base, and then there are a lot of sides, and each side basically has 3 nested sides, and this just keeps on going, and the deeper you nest, the more detail you're going to get in the fractal. I also did another one, and self-similar patterns are easier. This one is the Sierpinski carpet. This is basically a flexbox model, so I didn't have to do too many calculations, and it's just squares nested in each other, while the middle square is just not drawn. And to render this one, I only needed this much CSS. Putting more logic into this one, we could also create the Menger sponge, which is basically just a 3D version of the Sierpinski carpet. This one obviously needs more code and a little more logic, but the main stuff you might not be able to see, but right here in the middle, I put some continuing dots. So the main part is what happens while defining the 3-dimensional coordinate system. The good thing is that all these only have to be done once. So you have this code, and the deeper you nest your elements, the more detail you get in the fractals. So with this logic, I made a lot of fractals. I have an entire collection on CodePen. You can check it out here. And I want to show you a few. This is, for example, the reptile. We're going to see this in a live coding session later. Then I did the T-square. I also did a quadratic cross, and I made 2 versions of the cock snowflake. This one was really, really tricky to do, but I managed to actually implement it with the correct logic, because there's so many ways to draw this in CSS, but I wanted to get it mathematically correct. In the end, I just made a tree or a bush, and then I thought about implementing something that could be fun and that I could present at this talk. So I went for the Pythagoras tree, which is also a really, really nice and simple fractal. And this one is based on the Pythagorean theorem, which basically says that a squared plus b squared equals c squared. And this just means like the side of c, the square of the side of c and the square of the side of a and b, those combined, they're just the same. So in the end, you have the triangle in the middle. And now if we were to say that the triangle in the middle is a right isosceles triangle, we can actually use a trigonomic trick to calculate this. So we can just say that c divided by the square root of 2 equals a equals b. So how would this look in CSS? And this again is Sass. So if you don't know Sass, it's just a precompiler, and like the square root is basically just a function that calculates the square root. So I'm saying the nested size is 70.71% approximately of the parent element. So each element that's nested gets smaller and smaller. So we also need some simple properties. We're applying the height and the width to the element, then we're positioning it absolute, and we're pushing it from the bottom 100% up, so it's sitting on top of its parent, and then we're aligning all the elements to the left. The next thing we're doing is setting the transform origin, so the rotation angle is in the lower left-hand corner, and then we're just rotating it minus 45 degrees and giving it a background color. And in the end, it looks like this. But as I've mentioned, the simpler the CSS gets, the more DOM we need. And I'm not really happy with the performance or just the code that I need to generate with this. So I thought about how could I even simplify this thing. And I had this one idea. Because why not just simplify the tree to the half of one branch? So I'm just taking the base and only taking the half and then only generating a nesting of one element. And then we can apply WebKit box reflect. I hope you all know this. It's basically allowing me to reflect an element with all its descendants, which are the children. So while I add this one property, I actually can generate the entire tree from the same HTML that we saw before that only showed the one branch. Then we can go and add some coloring maybe, and this is an example. If you Google for Pythagoras tree and you go to Wikipedia, you're going to see this example. And depending on the depth, we can also rotate the color. And while we're rotating, we might even think about rotating this angle, and then we can generate a whole different fractal. And if we rotate it even more, it kind of looks like this logo from maybe World of Warcraft or some kind of clan, I don't know. And now if we would change the opacity depending on the depth, we can get stuff that looks even more impressive. And maybe we're just going to mirror this image, and then we can duplicate this. And we could also go and animate these. And this is kind of fun. I did this, and I guess you all know this guy. Tim Petuski from yesterday, and this is actually a picture from the JSConf. And when I was at the JSConf and I saw his talk, I went up to him and I talked to him. And I said, dude, I totally got to apply your stuff to my fractals. And I actually took some of his code from his first version of the Nerd Disco and made this example, and you're going to see it later. And what I did today is actually use his new version. So I sat together with him like 2 hours ago and took his ND audio thing and put it in my code. So really happy that it worked out. So I've shown you a lot of theoretical stuff, and maybe it was too fast of you, and I'm hoping it was, so I hope you're actually kind of confused. And I want to now show you this live. So I'm just going to switch to live coding. Oops. That's a spoiler, huh? I'm just going to put this over here so you can see what I'm actually doing and make this a little bigger. Can everybody see this? Yep. Okay. So I really like to use Jade because it just lets me create these a little with a little less coding and just adding a little logic. So right now I'm not nesting any elements. So it looks like this. And the deeper I nest these, so I'm going to put one inside. Now I get more of these. And I'm not changing anything in the code. I'm just nesting more and more elements. And I can get more detail from just the simple code. So I now want to show you how I did the same thing with the Pythagoras tree. Okay, so basically what we have right now is one element. Now let's take 2 more of these elements. And as I've said before, these are getting smaller. I'm pushing them to the top, and then I'm just aligning them to the left. So the next thing I'm going to do is rotate these. I'm going to start with the small nesting so you actually can see what's going on here. So now they're tilted. You can see how I got the picture from before. So now we can take a nesting of 12 elements. Now we get this one. And remember how I said I'm only adding one more property. This is the WebKit box reflect. And now I get this. So I didn't really do much in here. Yeah, and this was nice, but to me, this stuff is kind of boring. So I thought maybe it would be nice to put some animation inside. So now I'm able to rotate this, and you can already see how I got all the shapes from before. But this is still just something that's moving at the same speed, and it doesn't really do anything, and it doesn't change color, and it's just kind of boring. So I thought maybe we can change the background color depending on the depth. And then we get something like this. And right now I'm kind of bugged out by the middle white square, so let's remove this one. And it looks better and better. But I can also add some border radius. And remember, these are just duplicated elements, so now I'm getting more granularity because I'm splitting the element again. And I can also, depending on the depth of the nesting, I can change the animation duration. So what's happening now is that it still looks similar to before, but you're now going to see that it just moves apart, and it doesn't really have anything to do with the shape that you saw before. And it's really simple code. And because this is, well, it's nice to see this, but I thought, like I said before, it would be awesome to have this animated while listening to audio. Oh, there we go. So yeah, like I said, I'm using the code from Tim Petruski and just listening to the audio, and then I'm rotating all these elements and giving different colors depending on the frequency. I'm just gonna let this play so you can actually experience what's happening here. I could keep playing this because I love the song, but I don't want to bore you. And so if you're interested in stuff like this, you can follow me on Twitter, or you can look at my CodePen stuff. I have a whole lot of different experiments in CodePen. And I also have some stuff on GitHub, but I started putting most of my stuff on CodePen, so this is actually the place you want to look at. Oh, and there's one more thing. Dziękuję. So, any questions?
Well, that was amazing. Thank you. Can we have a second song?
Oh, sure. I mean, I can go back and just play another song if you want. So, any other questions or like totally blown hope? Hopefully.
Yeah.
Will you use it on tonight's party?
Excuse me?
Will you use it on tonight's party?
Will I use it where?
On the party.
I still didn't understand. Oh, I don't know if could be used, probably, yeah. I guess I basically do this just for fun, and I had this idea, and I don't know, I don't really use it anywhere, but sure, I mean this thing is also on CodePen, so if anybody's interested in this stuff, just look at my CodePen, or I'm gonna put these slides on later, and I put links for every example, so you can just look through it and maybe play with it. Yeah.
So I have a very practical question. So great stuff. But now that you animate all those elements, can you tell us like what properties really kill the performance?
What does really kill the performance? I did different examples with using CSS filters. Those are really, really hungry, and I removed those. I think, well, I reduced the number of elements. Basically, I only have 12 elements that I have to animate. So this is already a lot faster than having all these like nested elements. But I think basically the WebKit box reflect is really, really performance hungry. Like most of the WebKit stuff that's only implemented in WebKit is really performance hungry. It doesn't matter if it's the WebKit text stroke or all these things, just they're not really fast. And you could also see that there's some latency and it's not really on the timing. And this is also due to the performance. So the less elements I have, the more precise it gets from the sound.
Have you maybe considered or tried doing it in 3D, transforming this animation in 3D dimension?
I've thought about it. I did start making a few 3D fractals, but it's just basically the performance, it won't work. It's just, I could have like 2 elements and maybe animate this, but I think this is more impressive because all these patterns are actually due to having a low opacity, and then due to the overlay, I'm creating even more granular patterns, and that's why it actually looks this impressive.
Okay, thanks.
That's it? Okay, thanks.